and a happy new year to everybody. I will start my talk a little bit with explaining where I work and what I do. I have been part of BLiX since its beginning in 2009. BLiX is the Berlin Laboratory for Innovative X-ray Technologies, and it started off as an application and transfer laboratory for spectroscopy and imaging with soft and hard X-rays. And it's co-directed by two institutions in Berlin, the Technical University of Berlin, more specifically the work group of Professor Birgit Kangieser, and the Max Born Institute, which is a laser institution in Berlin. And what we do a lot is develop methodology, build spectrometers, and also give access to the instrumentation for research and education. And the motto was from the beginning on to develop the methodology which is routinely done at synchrotron radiation facilities in such a way that we can do that also in the laboratory. So from the synchrotron into the laboratory, very similar to the work Jerry is doing. And now in the last year, we are completing the circle and we go back to the synchrotron. We have established a joint research group between the BLiX and the synchrotron radiation facility BESSI in Berlin, which is run by the Helmholtz Zentrum Berlin, and where I'm employed now. And what we want to do there is look at the synergies which are offered by using both laboratory and synchrotron instrumentation. And this is really a statement from the synchrotron radiation facility that they start acknowledging all the work we've been doing in building these spectrometers in the laboratory. And going back to the BLiX, here's a bit of a list of what we have as instrumentation at the Technical University of Berlin, to give you an idea that it's not only X-ray absorption spectroscopy. We started off with X-ray fluorescence spectroscopy, elemental imaging in 1, 2, 3 dimension with micro-XAF and confocal micro-XAF. We've been doing grazing incidence and grazing exit X-ray fluorescence for elemental depth profiling in the nanometer regime. We have an X-ray microscope operating in the water window, which you see up here. And a large part of the group is also dealing with chemical speciation. You have already heard 2 talks from our group. The first one was from Richard Gnevko, and he talked about the X-ray emission spectrometer for the hard X-ray range, and Wolfgang Meitzer then talked about the X-ray absorption spectrometers. Both spectrometers use Van Hamos schemes and HAP-G optics. And today I will go a bit softer. I will talk about our NEXAFS spectrometer in the soft X-ray range, which is a twin beam transmission spectrometer. And in my talk, I will start with some general comments concerning soft X-ray absorption spectroscopy, then show you the setup and the characteristics and performance of the spectrometer, and then finish with some new stuff we've been doing: quick X-ray absorption, fine structure spectroscopy with CMOS cameras, and I will end with optical-pump soft X-ray probe spectroscopy on thin organic films. So soft X-rays, when I say soft X-rays, I mean the energetic range between 200 eV and about 1.3 keV. And here's just a little sketch to let you know what absorption edges we can look at in this energetic range. And from our in-house research, we're looking at organic molecules, and there we're mostly interested in the K edges of carbon, nitrogen, and oxygen, and also at the L edges of transition metals, but you can look at a lot of M edges also in this range. But for sure, it's very interesting, especially for the K edges. And a typical carbon spectrum collected with our spectrometer is shown here. This is the carbon K edge of a C60 thin film. And there's also a near edge region where you have a lot of resonances, which is in the soft X-ray regime a couple of tens of EV. And then you could also look at the EXAFS region, which is not very often performed because it's just easier to do EXAFS in the hard X-rays. And but this is a typical soft X-ray spectrum. And as fluorescence yields are very low in the soft X-ray range, for bulk analysis transmission mode spectrometers are more advantageous. But bulk in these low energies means that you need samples which are a few hundred of nanometers thick, which makes the sample preparation one main challenge in doing interesting experiments. The commonly used scheme at synchrotron radiation facilities is that you monochromatize your polychromatic radiation, then transmit through a sample and detect the intensity. But for most laboratory spectrometers, the second scheme is used, where you first transmit your light through a sample and then use dispersive optics and a detector. And for the soft X-ray range, there are challenges, many instrumental challenges, starting with the sources, because already the sources are not readily available, and you really need brilliant sources to have efficient spectrometers. You always have to use vacuum instrumentation. You have to look at the efficiency of your optics in this range, and also the detectors, especially if you want to use imaging detectors, still have some optimization possibilities. Here you see now the general layout of our system. We're using as a source jointly developed laser-produced plasma source. That means that you use a short, intense laser pulse and focus that onto a target material where a hot, dense plasma is formed, and this plasma emits the desired radiation. And you can tune your radiation by changing the laser parameters and the target parameters. Such sources are very bright, and they're more like a light bulb than a laser. So the emission is isotropic and not coherent, but as I said, very bright. We can, in our spectrometer, we use the possibility to use a large solid angle and have 3 arms. We have one arm, a pinhole camera for monitoring the source and for correction mechanisms, and we have 2 arms where we have the dispersive optics, which focus the light onto one large area CCD, and we insert the sample in one arm and a reference in the other arm, so we can do single shot spectroscopy. By using only one shot of a laser, we get a full spectrum on our CCD camera. And because we have a laser-based source, we can take a little bit of our laser intensity, delay between pump and probe pulse, and also change the wavelength to optically pump our sample. And in the following, I will go through all the components of this setup in more detail. So let's start with the source. We're using a modified ytterbium YAG thin disk laser system by the company Trumpf, where we had to change the seed diet to have pulse durations in the nanosecond range, and actual plasma chamber was built together with a small company in Berlin called Bestec. And here's the source chamber, and this is a view of the virgin chamber. It looks a lot different now due to the ablation of material in the plasma. The laser beam is focused from down here onto a massive metal cylinder with the base metal copper, and so that the laser beam always sees a fresh spot on the surface, we rotate and translate the cylinder, and here the plasma is formed, and we have two beamlines, which are shown here. Also, this is one beamline, this is the other beamline. This is a quite old photograph. It looks a bit different now because our twin beam spectrometer is now attached to this arm and goes for 4 meters into this direction. We built this source with the design goals that it's really flexible and reliable, that we don't always have to, that we don't have to be the laser experts, but we really use the soft X-rays, and it is possible to use the source 8 hours a day and 5 days a week. And it is, when using the copper as target material, and also quite affordable operation. What we get is shown here. These are example spectra from our two common materials. In red, you see a copper emission spectrum, and in black, you see a tungsten emission spectrum. And they're very different due to the plasma physics. So in the plasma, the atoms are ionized to a very high degree, and they then have a lot of different pathways to relaxate. And for high Z elements like tungsten, you have so many relaxation lines that you get unresolved transition areas, which almost look like continuous spectra. And in the copper spectrum, you still see the distinct relaxation lines. And both materials are needed for a NEXAFS experiment because the copper spectrum is very good for alignment of our optics and also for the derivation of the energetic resolution. And then the tungsten spectrum is used in order to generate the NEXAFS spectrum. We have the possibility to use other target materials as well. Here's just a selection: gold, tantalum, tin, palladium, copper, kapton. And this is quite nice because depending on where your absorption edge lies, which you want to look at, you can tune your emission spectrum. The laser operates at 100 Hertz. So we can do experiments at 100 Hertz, and we can tune the laser pulse duration between 500 picoseconds and 30 nanoseconds. We have a source size of about 50 times 15 microns, which results in brilliance values of 10 to the 10 to 10 to the 12 photons per second, millimeter square, millirad square in 0.1% bandwidth, which I don't really like to say actually, because this is just a number. I think the more interesting number is how many photons we have in an energetic channel on our CCD in the end, because that is something you can work with and calculate how many shots you need for a specific statistic. Okay, we get such a spectrum in one single shot. So you have the polychromatic radiation in the 500 picoseconds or 1 nanoseconds, and this you transmit them through a sample. And the sample must be quite thin, so it has to be about in the range of a few hundred nanometers thin if you're using solid state samples. And we typically use silicon nitride windows as frames and base material, and with 150 nanometer thickness and quite a large area. So 1 times 1 or 2 times 2 square millimeters, because when going back, the size of the sample immediately restricts the amount of radiation on the optic and then on the CCD. So the larger our sample is, the more light we have, so the more efficient our spectrometer is. But that also means that we have to have homogeneous samples over a large area, which we usually prepare with an diffusion cell, where we evaporate molecules, or we can do spin coating, and if everything fails, you can use dried droplets, which is not very not the best way. And these are two examples. That's a molecule I will be talking about later on. Also, this is organic molecule which forms beautiful homogeneous layers through evaporation. And this is an example of a spin-coated titanium dioxide film, both in the range of 150 nanometers thick. We also are developing something like liquid cell, but this is still not finished, this development, because as I said, the area is quite large, so you have to contain the liquid between two windows and also prevent the windows from bulging, which makes this development quite challenging. For the samples, we have quite some characterization methods in the lab. We have UV-vis spectroscopy and thickness determination using EUV transmission experiments. We do, for probe spectroscopy, we need nonlinear transmission experiments, which I will be talking later on also about. And at the Technical University, we have access to atomic force microscopy, but also scanning electron microscopy. So the more you know about your sample beforehand, the better. Okay, so the radiation is transmitted through the sample and then hits our optics chamber. So this is a view from the source. Here is the sample chamber. Here are the optics, and in the back is the CCD. And as optics, we're using reflection zone plates, which you see here. We have 2 times 4 zone plates, which are designed for the energies of the carbon K edge, nitrogen K edge, oxygen K edge, and copper L edges. And in the spectrometer, they are facing each other in the optics chamber. And these structures work, as you see here. You have a source, then you have your zone plate, and we're using in these reflection zone plates an off-axis part of the zone plate, only this part here. And this part then focuses the radiation onto the optical axis, which is shown here. And as you see here in the scheme, on the CCD image, you only have one energy highly resolved. The others are broadened. And this is a ray tracing of such an optic. This is the optic for the carbon K edge with the copper spectrum. And you see that the energy resolution is here, very nice, but degrades very fast to higher energies. This is the 1 keV region. But by misaligning the structures, you can shift the area where the energy resolution is highest to different energetic regions, as shown here. Here, the best energy resolution is in the 1 keV range. And this is only by changing the incident angle onto the reflection zone plate by 1 degree. So by using our 4 optics, we can easily investigate the whole energetic range of our source from about 200 to 1.3 keV. And the resolving power is about 900 or a bit more over the whole range. The reflectivity is about 10 to 17%. And when using the copper emission spectrum, we can have an uncertainty in the absolute energy calibration of about 0.2. And this is then a typical titanium dioxide L-edge spectrum of the sample I showed you here, I think. And this comes This is generated in such a way. This is a CCD camera image. You see the source image in the image of the source in the middle, which is used for monitoring, but also for an online adjustment of the source. And you see here the reference spectrum of a tungsten measurement, and the energy axis goes for the reference spectrum in this direction and for the sample spectrum in this direction, because the optics are facing each other in our optics chamber. And then you just have to generate the spectra to get the absorption spectrum. This image looks a bit distorted because we're binning 8-fold in order to reduce the readout time as much as possible, which is really a limiting factor with CCD cameras. Okay, here just one short slide about the pump beamline. We have a delay stage where we can continuously tune the delay between pump and probe in the range of 3 nanoseconds, but we can extend the delay at least up to 40 nanoseconds when using our whole laboratory once, but if we use it a few more times, we can go even further. And we have some nonlinear crystals and a dye laser in order to tune the wavelength between 343 nanometers to our laser wavelength of 1030. Okay, I will take the first break for questions here.
What a great start. That's wonderful apparatus. There's several questions. First one is, you say you have an upper bound of about 1300 EVs. Is that due to the plasma or due to the zone plate limitations?
And to the plasma, or okay. More precisely, it's due to the pulse length of our laser. If we go a bit further, we have a very similar setup at the Max Born Institute, where Holger Stier is using 2 picosecond laser, which is a lot more complex laser system. He can go, I think, to 1.5 or 1.6 keV.
I see, a little bit higher.
It's a little bit higher. It doesn't go at some point. It's then the benefit of the laser plasma source is then not large enough. Then you can also go to, for example, femtosecond laser plasma sources or X-ray tubes or other things. So
I see.
Yeah.
Okay. What's the typical bandwidth of one zone plate, and is there any possible trade-offs between bandwidth and energy resolution?
I will be talking about the characteristics in a few slides, and I think the question will be answered there.
Very good. We also have a question from Joshua Weiss. He wants to know, what are the limits of pushing to shorter pulses? Is 500 picosecond lower limit because you can't get shorter 200 millijoule pulses without really big lasers, or is it a limit from the plasma emission?
I think the first, as I said, at the Max Born Institute, we have with 2 picosecond lasers a very similar source. So if you go to different laser systems, you can go shorter. If you go then even shorter, the physics in the plasma change. So I think 2 like picosecond to nanosecond range, the physics of the plasma is still very similar. If you go shorter, other effects take over, and then you get more hard X-rays and not soft X-rays anymore.
Okay.
But it is already our system. When we bought it, was designed for 10 nanoseconds. So it is not easy to get lasers with 1 nanosecond or 500 picoseconds with such high energies.
Got it. I understand. There's a question. What can you tell us about your liquid cell effort?
We're totally in the middle. We have a very promising cell where we are. This is I think also done in a few other cells using helium atmosphere to prevent the bulging of the windows, but we found that this we hoped that a passive pressure equalization system would work, but we're still optimizing the design of the spacer, because
just
you always have to have some sort of spacer between the two windows.
Right.
And yeah, we're very in the middle.
So just to elaborate on that, what you're talking about is essentially having 4 windows: an entrance window, a helium space, 2 windows around the liquid, a helium space, and an exit window, yes?
Correct.
Okay, you know that there was this wonderful review article recently by the group in Japan that's done a lot of that. Do you happen to remember the name of the group so we can have that for people who might be curious?
Not out of my head.
I'll try to look it up and put it into the chat, but it is a wonderful article summarizing more than 10 years of work by this group on Japan.
They have very, very interesting and working examples, but the problem always is for us that we can't use that because they're only using a very small part of their window.
That's what I was going to ask. It sounds like a lot of your trouble is that your spot size is not small. How big is this spot size on the sample?
Basically, the spot size is the window size. We don't restrict any additionally. The larger the window size, the more photons we have in the end. So
I understand.
In principle, what we aim to have is a homogeneous thickness for a millimeter, and this is quite a challenge.
I understand. Okay, I don't see any more questions, so you should continue. Thank you.
Okay, thank you. So then coming to the characteristics, I put in one old slide. This is from our first single shot publication in 2016, where we didn't have the twin beam set up yet, but this shows a little bit something about the question about the zone plates. This is the emission of the copper spectrum imaged with 2 different zone plates, which are both aligned to their respective design energy. So this is in turquoise the carbon emission, and in black the nitrogen K zone plate. And you see here on top the resolving power. So the resolving power is quite high for about 50 EV, maybe a bit more, but then degrades to both sides, which is also seen in the nitrogen K edge. And these 50 EV are, for our purposes, for the NEXAFS measurements, have always been sufficient. There is a trick where you can enhance the energetic range where the resolution is higher, which I will talk about later on also. And there is also research going on right now to change a little bit the geometry of the zone plates and not write them on flat surfaces, but on bent surfaces, which would make it possible to really have a high resolving power over the whole energetic range. And okay, this was the zone plates, and this is the example, more or less the most optimal sample you can imagine. This was a thin polyimide foil, which was large and completely homogeneous. And what you see here in blue is the spectrum in 1 nanosecond shot. So this is a single shot spectrum where you already see all the interesting transitions in this spectrum. The red, the graph here is the average of 15 pulses, and we did in this publication a comparison to synchrotron spectrum, which essentially looked the same. What is also really nice about this picture here is that because we know all these relaxation lines, we always have during the measurement our absolute energy calibration. We don't need to calibrate every few weeks or months our beamline, but we know for each measurement the energy calibration, and there the uncertainty is for the most energetic range about 0.2 eV. So this was the beginning of our single shot spectroscopy, and this is how the performance looks like now. This is again the titanium dioxide sample, and in this graph you see the measurement of the titanium L edges, in red single shot and in black a few hundreds of shots averaged. Here you see the oxygen K edge, and if you adjust the zone plate to the titanium L edge in normal operation, the resolution at the oxygen K edge is really bad. But what you can do is you can reduce the aperture in your beamline, and then you can image a very much larger energetic range, which you see here with quite high energetic resolution at the cost of photons, because you're limiting the number of photons. But this black spectrum also only took 2,000 single shots, and if you would be able to do it really at 100 Hertz, that's really not a long time. So these spectra are in an energy range which are already is already available with harmonic generation also in the laboratory. But what is really unique for our spectrometer is that we can go quite a lot higher, and this is the copper L edges, and this is like our really the end of the magnesium K edge at 1.3 keV, and this black line is the only smooth curve I show today. So all the others are just the real measurement, but at the magnesium K edge really are counting the photons. So we can go to quite high energies for a soft X-ray source and NEXAFS system with about 900 resolving power of about 900. And if you look at this, in principle, also EXAFS is possible with this setup if it's interesting for anybody. Okay, and when you have such nice spectra, you also want to look at some numbers, and we wanted to look at statistics. And in this graph, you see in red the tungsten emission spectrum for a specific energetic range, and in gray the measured noise of about 500 images, and in black you see the calculated noise from the emission spectrum. And the agreement of these two curves shows you that the spectrometer is essentially Poisson noise limited. So we really only have to look at how many photons we have. We don't have other really significant noise sources. That means that we can calculate how many shots of our source we need in order to have a specific certainty in our spectra. And also then, especially for probe spectroscopy, to know how small can the changes be we're detecting or measuring in different spectra. And this is shown here. This is a calculation for two examples of photon numbers per channel, which we have on the CCD, starting with red 500 photons per channel or 5,000 photons per channel, which is like a little bit the variation also shown here in this energetic range. And it's calculated for 3 cases of samples with different mood-Ds. And you see that to get to an uncertainty of 10⁻�3, you need about 3 to 6 hours. with our conventional CCD camera. In numbers, that means we have an accuracy in one single shot of about, in the percent range, in 60 millieV on the carbon KH. And these 6 hours, if we could exploit our 100 Hertz laser system, and which is really limited by the readout speed of the CCD camera, and use, for example, CMOS technology, this would immediately be reduced to 1.2 minutes, which is a crazy factor. So we were very, very interested in using CMOS technology. And we purchased a camera by G-Pixel, which was not adapted for soft X-rays. We had to remove a window and attach a vacuum flange, and we managed to do really 100 Hertz spectroscopy by selecting a region of interest, because the camera can only do, I think, 48 frames per second, but by reducing the region of interest, 100 Hertz is possible. The camera at that point was still not that user-friendly, so we had some difficulties in the also in the timing and stuff like that, but it did work. So the technology does work already. It just needs the manufacturers to fully develop it. And this is an example at the nickel L edges, where you see a single shot and then different accumulations up to 20,000 shots. And here these two are a comparison between, in red, the CMOS, and in black, the CCD camera at 1,000 shots. And by the naked eye, you can't really distinguish any statistical uncertainties. When looking at it in detail, you see that there is a slight offset still in the CMOS camera images, which is due to the different gain characteristics of the different readout units on the CMOS camera, but this is something also manufacturers can get rid of. So we're very excited to see what the next, what already is there and what is now developed in this technology. And concerning what you can do with this then is what we called quick X-ray absorption fine spectroscopy, similar to the things done in the hard X-ray range, because already in the single shot, if you only want to look at shifts in the absorption edge energy or something like that, this might be enough, and then you could really use the 100 Hertz to look at dynamics with 10 millisecond resolution. If you have to accumulate a few shots, I don't know, 100 to have a very nice spectrum, as seen here in the purple, you would have a time resolution of 1 second, which is also still interesting for slow catalytic reactions, for example, or thermal processes, or thin film growth, sample monitoring. There are a lot of possibilities which then can be in the millisecond to second to minute range, which could be investigated. Okay, I think now's the second break before I come to the optical pump soft X-ray probe spectroscopy. Are there any questions?
Yes, hi, sorry, my microphone was up. If you can go back one slide to the one with the 100 Hertz. Yeah. I got a little bit lost. The 100 Hertz, that's just for single shot being able to see the edge, is that right?
This spectrum is a single shot.
So okay, so that's what you could do at 100 Hertz, yes?
Exactly, yeah.
Excellent.
This is a bit unfair also, because at nickel we don't really have that many photons. If you would go to different edges, the spectra look nicer, and it always depends also on the sample, how well the spectra look like.
Of course. I wanted to point out that I think Oxford has a new soft X-ray CMOS camera that they just released the specifications on last week or 2 weeks ago.
Okay.
And you might take a look at that, or you can email me and I'll tell you. I've forgotten the brand name. But yeah, there's at least one other actually soft X-ray CMOS camera that's becoming available.
Yeah, they're starting. I think Ender is also starting. So it's really a very rapidly changing field, I think.
Yes.
What cameras are available, and that's really nice.
Good. Wan Li, you have a question?
Yes, thank you. Great talk. So it's a very quick question. If you use the current CCD, what is the energy range you could cover across the CCD area? If you don't rotate your zone plate, if you don't touch your optics, or what's the energy range this covers?
It's about 150 eV, something like that, which we can. It also depends on what part of the spectrum we are, but it's over 100 EV. It's between 100 and 200 EV, depending on the energy, which can be imaged on on the CMOS, which is only a slightly bit smaller than the CCD camera we're using.
Okay, thanks.
Dugan, you have a question?
Yeah, I was just wondering, you show you mentioned all these exciting possibilities that the single shot quick-XAFS makes possible. One thing I'm wondering about that might be maybe a little too challenging for the near future is operando electrochemical measurements. Once you get the liquid cell working, is that something you're thinking about? What do you think the prospects for that are?
We are thinking, we're not. I think the challenge is really to build a cell which would mimic something which is really meaningful for the applications. As I said, we're still working on the liquid cell, and I think other options are easier to reach than really having some electrochemical or battery or something like that. So it's challenging to go there, especially with a large area.
Yeah, sure.
But sure, we're if this works with the liquid cell, there will be a lot of new paths which we can look at. And I think it's also, we are building the spectrometer, but we don't, from our in-house research, have hundreds of research questions. So if people come and say, okay, we want to measure exactly this, then you can adapt the instrumentation. And if there's interest, there can always be cooperation on specific topics.
All right, great.
Yeah.
Thank you.
Adam, you have a question?
Yeah, could you comment on the performance of that system, the Ioanna system, CMOS for the carbon 1sh?
Do you have some specific?
Well, have you measured at the carbon 1sh? And, is its performance what you expect, or is there limitations?
It's very similar as here shown for the nickel L edges. We have done also experiments at the carbon K edge, and it's basically it's really only for this camera still that the noise is a bit higher than when using CCD cameras. And that the software is interesting to handle, but for the rest, the efficiency and sensitivity are very similar to the CCD camera.
Okay, thank you very much.
All right, you should continue. Thank you.
Okay. So optical pump soft X-ray probe for our organic molecules look a bit like this. You have molecules where you have highest occupied molecular orbital and a lowest unoccupied molecular orbital, and you excite electrons between the HOMO and the LUMO, and through this new vacancies are created, which can then be probed by our NEXAFS spectroscopy. So what we expect when we optically pump such molecules is that we see some features rising and some features declining. This here you see it also in a bit nicer scheme. We excite from the from the ground state to one of the unoccupied molecular orbitals. They relax very fast to the first unoccupied molecular orbital. These relaxations and the excitation we cannot see with picosecond to nanosecond, but then what happens then is something that might be possible to image with our system. For example, inter-system crossings, what happens in large molecules, electronic transport, and also other things can be seen in the nanosecond range, talking about diffusion or chemical reactions, but also for solid states, lattice vibrations and recombinations. And these are phenomena we can try to see with our system. And our first example was this nice molecule called TAP, which is an aromatic molecule with a typical ring structure. It has 4 Boutu groups, and it does not have a metal center, so it's metal free. And it can be prepared into very homogeneous films, which is really a prerequisite for us. And here you see the UV-Vis difference spectra between liquid and thin film TAP, which do change due to the different environment, but that do not change so much that we are quite positive that there is no molecular damage when evaporating these films. And with these UV-Vis, you can then select a wavelength which optimally excites your sample and do nonlinear transmission experiments. These experiments are performed by changing the photon flux density on your sample and looking at the optical transmission at the pump wavelength. And usually the transmission should stay linear, and at some point these curves become non-linear, and that is the point where a substantial amount of molecules are excited. So this is where we want to be at with our photon flux density in the experiment. And on the left side here, you see the experiment on liquid samples, and you see that you can tune your photon flux density over a whole wide range and get really large changes in your transmission. This is 20%, this is 40%, so by a factor of 2. But going to solid samples looks immediately a bit different due to heat transport problems. So the challenge is to make a sample that can be excited in a way that a substantial amount of molecules are excited, but that does not is not damaged yet. So you see that we have to stop a lot earlier than for the liquid samples, and the changes here in the transmission are only a few %. So it is from the experimental part concerning the sample more difficult to do it on thin films than on liquids. Just the sample preparation is different. But in this case, we used something like 1 × 10⁻25 photons per second and square centimeters for pump probe experiment. And here you see the results. We did change the pump probe delay between negative delay and up to 43 nanoseconds. And there are changes, and the changes can be seen here. In purple, you see our NEXAFS spectrum, and the dashed line is a DFT calculation, which agrees concerning the energetic positions very well with our experiment. In gray, you see the negative delay, and in black, the positive delays. And you see that there are changes around features A and B, which through the DFT simulation we know are associated with carbon atoms which are bound to nitrogen. And you don't see any changes in the carbon atoms in the butyl groups. So it's really happening in the aromatic ring. And what we can also see is that this excitation is really long-lived. It's more than 50 nanoseconds. And this example was really a tough one, because here you see the scale of the differences. So that these differences are in the range of 10 to the minus 3, low 10 to the minus 3 to 10 to the minus 4. So you really, really need a very stable setup to be able to measure something like that. And we were very happy that it worked. A bit easier example was a molecule called FHBT. This is a molecule routinely used for organic electronics like transistors and light emitting diodes. And here you see again the results of our pump probe spectroscopy. You see in red and behind that in black the static and pumped spectrum. And this is the difference. And this was very nice because you see that the spectrum basically does not change except this one feature, which is shifted to lower energies. And such a shift can be detected a lot easier. So you get immediately differences in the percent range, which is a lot easier to manage. Yeah, we know that this feature is associated with the carbon atoms in the alkyl change, but we're still in the middle of looking into it, what this could mean. And last example is this beautiful C60 spectrum I showed in the beginning. In a collaboration with Friedrich Roth and Wolfgang Eberhard, we looked at pump probe differences in the plane C60 as prepared as a thin film. And here you see our results, which show a broadening to the lower energy of a few of these features, which was also measured at ALS in Berkeley. And we could manage to see this, although they proved saw there that these changes have time constants in the 100, oh no, it's nanoseconds, sorry, in the 100 nanosecond range. Okay, these are some examples. So we have seen and optimized our experiments for a couple of organic films and other thin films, and I really want to stress a little bit more the advantages of such a laser-based laboratory system, which I think only recently come to understand, because I'm doing more experiments back at the synchrotron again. We built this spectrometer in order to get as many photons as possible on our CCD and get as much efficient, as much as efficient as possible. But at the same time, we build it in a way that we have minimal radiation dose on our sample. So not only the soft X-rays, but also the laser is directed on a large area, which makes a lot of things like heat transport and lower radiation doses possible. And by using this the scheme that you always measure reference and sample at the same time, you can monitor sample degradation at each shot. You can really see what is happening not only at one specific energy with your sample, but you always get the whole spectrum and can see changes due to the laser damage or X-ray damage or something like that. And what is also quite unique for these laser-based systems is that you really only have light on your sample when you do the experiment. There is no background in between the pulses. And with this, I think, yeah, this is my last slide. I showed you our really stable and efficient spectrometer, and we're doing, we can routinely do NEXAFS measurements in a range from 200 eV to 1.3 keV, and right now are very interested in dynamics from nanoseconds to seconds or minutes. So if anybody has an interesting question at hand, please feel free to contact me. But for sure, we are also working to further optimize the system. I told you that there are possibilities to build these zone plates onto curved substrates, which would enhance the energetic resolution. We are closely looking at the CMOS technology and also at the liquid sample development. And what also is, I think, very important in the long run is to combine the different time domains from different sources to get a full picture of the dynamics in dynamics in pump probe spectroscopy. So to combine efforts at synchrotron, harmonic generation sources, lab-based sources which have longer delays, and so on. And the most important people for this work was in the beginning Katharina Witte, who did the first NEXAFS measurements with our source, and now the PhD thesis of Adrian Jonas, who built up the twin beam spectrometer, and all the other people who are listed here, Birgit Kangieser and Holger Stiel, who is the responsible scientist from the Max Born Institute. And with this, I thank you for your attention. And if there are any questions left, please shoot.
Oh, there's always questions left. First Jacinto, and then after that, Adam.
Hi, Nina. One thing I would like to ask you, do you think it's possible to do the other way around, like X-ray pump and optical probe? Like, for example, if you think of the titanium where you would pump the valence electrons from with the X-rays and then look at the dynamics with the optical, because that has this clear relaxation on the optical because you cannot longer excite the valence electrons in the same way.
Good question. It depends. I mean, in principle, yes. You can also monochromatize the spectrum to also do that resonantly, probably. It would be...
I would even think like non-resonant. I mean, as a way to mimic, for example, if you can think of titanium like as a semiconductor that you pump and you take the electron out to do something in the chemical reaction, but then the hole is left behind and you want to know what's the dynamics of that hole. One way to mimic that is actually you eject the electron with X-ray. That means if we just send X-rays with enough energy to take the electron out, and then optically measure what is the change on the valence with that electron. So, because it's quite tricky to measure hole dynamics. I mean, even the other optical methods are quite tricky. And in this way would be a very clean way to create a very localized hole. And then we know that optically this will change the absorption spectrum.
Yeah. In our setup right now, it's not possible because, but we have been thinking, because we excite the laser beam path is just with mirrors, but we have been thinking of doing that with optical fibers also, which would make such an experiment, I think, quite possible. We've never thought about it before, but let's keep thinking about that.
Yeah. Good.
Okay, Adam, you have a question?
Yeah, I was just wondering if you have any plans for commercialization. Is that a path that your lab might go?
We are building right now a very similar system for a different research institute in Germany, for Max Planck Institute, which is in the form of a cooperation project. We have had very much difficulties also in other regions of our experiments to get any help or funding in Germany for doing something concerning commercialization. So not really, it's not really something on the list. It is sad that it's really difficult to do in Germany because we have tried in the past, but I think right now we're more trying to get more cooperation projects and things like that. But it's not excluded if there would be really some sort of market and commercial possibilities. I think we would be interested also.
Thank you. I'm sure there's a market. The question is to bridge from the development of the instrumentation to commercialization.
And to get the starting money.
Mm-hmm.